Alright, so in this video I'm gonna be explaining another important article with the title PANDA, expanded with aware message passing beyond rewiring. Because we use rewiring to avoid over-squashing in graph neural networks. Here they introduce a new model called PANDA in this paper in ICML 2024. So recent research in the field of graph neural network has identified a critical issue known as over-squashing, resulting from the bottleneck phenomenon in graph structures, which impedes the propagation of long-range information. Prior works have proposed a variety of graph rewiring concepts that aim at optimizing the spatial or spectral properties of graphs to promote the signal propagation. However, such approaches inevitably deteriorate the original graph topology, which may lead to distortion of information flow. Whenever, for example, you do rewiring, those kind of things, you're changing the topology. That is the motivation. So let's look at the idea. To address this issue, we introduce an expanded with-aware message passing, a new message passing paradigm where nodes with high centrality, a potential source of over-squashing, are selectively expanded in width to encapsulate the growing influx of signals from distant nodes. So you see the potential pitfalls here, for example, in a molecular graph, that rewiring the edge, for example, between carbon and oxygen, in red to a benzene ring violates the domain knowledge. Maybe carbon and oxygen shouldn't be connected. And so in social graph, another example, connecting a user to his or her enemy may lead to totally different meaning. So it's not naturally or intrinsically possible. And for comparison of resistance correlation and mean accuracy, you can see this graph. So we have a natural question. Is it possible to design a message passing that enables information exchange between nodes with different width only in a way that mitigates over-squashing without rewiring? We propose a new message passing framework that addresses the above question. First, the entire node set is divided into two sets, expanded and non-expanded nodes, color red and blue, for example. Then we classify 4 different edge types depending on the expansion rate, state of the node at the source and target position. Low to low, high to high, low to high, high to low. There are different kinds of nodes. So red, for example, is high, and then blue is low. So you see different configurations. For each kind of edge, we want to have a different kind of message passing, as you will see. So the message passing for GNN, you're familiar with this. We call this aggregation of these neighbor nodes. And then here we have update. So we know over-squashing in different papers, especially Topping 2022, we know about that there is an upper bound for this gradient of one node with respect to another one. Of course, one node could be in a different layer, like layer L, and different node could be in the initial node. So It all depends on the topology, also the modeling. For this motivation, now we can see why we use this method. Of course, there are other methods like effective resistance, but computation of this is very computational expensive, is high. And then you should go solve a linear system of equations. That's why they just use the concept of node centrality, which is very easy to calculate. So they define the neighbors, as I said, like this. That B is if one is among the top k nodes in that centrality nodes that you have selected, then we call it's 1. Otherwise, it's 0. So we are distinguishing between nodes. We only have 2 types of nodes. Those that are very central, those are ordinary. So we have this binary mask, and we use it to define our neighborhood from low to low, from high to low, from high to high, from low to high. And so that is the method of PANDA. So let's do some reflection to see, is this an interesting natural method or not? Well, do you really think that in your brain you distinguish nodes by their centrality? So you only have low and high. So these are the message passings that they go from low to low, high to high, low to high, high to low, and then they aggregate all of these types of nodes, maybe concatenation of all of them. Because we concatenate, we are respecting the nature of them. For example, low to low message is very different from low to high message. But because for each node, the neighbors could be anything, some of them could be like this, some of them could be high to low, or low to high, or high to high, low to low. Because the nature of this, we need to aggregate combine all of these different types of information. That's interesting. That's very, very interesting. So F is a linear transformation that projects node features to expanded dimensional space. And then we define this G as a dimension selector. So to better understand our framework, we show how to integrate PANDA into 2 classical message passing neural networks, namely graph convolution networks and graph isomorphism network. They can also use it on graph attention and many different variations. So the layer update is expressed as this for low and high dimensional nodes. First, if the node V is low dimensional, then if node V is high dimensional. So you see that high to high, high to low. If node is low dimensional, so low to low, low to high. So if this is low, so the neighbors could be either this, and if the node, central node is high, so the neighbors can be high and some of them low. So that's why we need high to low and high to high, like this, high to high, high to low. Because different kinds of messages are coming from source to the target nodes. And then they did on these benchmarks mu tag Enzyme is really hard, state of the art, still very low. For PANDA, it's just 46%. Protein is easy, is an easy data set, so it's 75%. Colab, they use it for Cora, Colab, PubMed. These are for node classification. So most of them are graph classification, but they did the rewiring based on this method.